Hello, my name is Jeff Christians. I'm a second-year graduate student in the Kamat Lab, and today I'd like to talk to you about measuring photoelectrochemical performance of quantum dot solar cells, interpreting 2 and 3 electrode measurements. So let's get started with some of the instrumentation used in these measurements. These measurements are generally conducted using a potentiostat. A potentiostat is simply an instrument that measures the current between 2 electrodes when you apply a potential between those. When the potential of the electrode is higher or more negative than the electrolyte solution, electrons can flow from the electrode into the solution, causing a reduction of the solution. And likewise, when the electrode is more positive than the solution or lower, electrons flow from the solution into the electrode, causing an oxidation. Now, if we think of the case where we have 2 ideal electrodes immersed in an electrolyte solution that has some resistance R, as shown on the right, we expect to obtain an ohmic response, V equals IR. So the IV curve would be linear with a slope of RS, the resistance of the solution. Now, if we do this same experiment with real electrodes, we get this V equals IR ohmic response over a limited current window. But at high currents, the response deviates from this linear response of 2 ideal electrodes, and this deviation from ideality is what we call electrode polarization. So electrode polarization also happens in the counterelectrode of our solar cells. An ideal non-polarizable counterelectrode would be able to pass any amount of current right at the reduction potential of the redox couple. However, real counterelectrodes can't do that. They're polarizable. Therefore, depending on how well suited the counterelectrode is to reduction of the redox couple, we need to apply an extra voltage in order to pass the desired current. So this extra voltage that needs to be applied is what we term the overpotential. And all overpotential is the difference between the thermodynamic potential of a reaction and the actual potential at which that reaction occurs. As seen below, to pass the desired current, we must apply the thermodynamic potential of this reaction plus delta V, which is our overpotential. So overpotential can be caused by a variety of different factors, some of which are electron transfer across a charged double layer that builds up between the electrolyte and electrode, any reactions that must occur before electron transfer can occur, depletion of electrolyte concentration at the electrode surface, and other factors as well. In general, it can be minimized by selecting the appropriate electrode material for use with your redox couple, but it will always be there to some extent. So another important concept in semiconductor physics and in understanding solar cell operation is the Fermi level. So the Fermi level is a pseudo state that has a 50% probability of being occupied by an electron. And what that means is that it's a measure of the potential energy of electrons in a solid. In semiconductors, it lies often between the valence band and conduction band and doesn't necessarily correspond with an actual electronic state in the material. It's a pseudo state. So in the examples below, we see that as we increase the relative populations of electrons in the conduction band, we can move our Fermi level higher, closer towards the conduction band. If we have more holes in the valence band, we move the Fermi level lower or more positive, closer to the valence band. So in our quantum dot solar cells, we're often constructing them with semiconductor heterojunctions, so 2 semiconductors in contact, such as a TiO2 electrode coated with QDSC. And when we bring 2 semiconductors with different Fermi levels into contact with one another, we see both hole transfer and electron transfer such that the Fermi levels reach an equilibrium. So there is one common Fermi level across the entire composite. Now that we have a basic understanding of some of the physics needed to understand solar cell performance, let's look at the different measurement techniques that we can measure our solar cells with. So electrochemical measurements are generally performed using either a 2 or 3 electrode configuration. In a 2 electrode cell, you have a working electrode, which is generally our photoactive electrode, and a counter electrode, which regenerates our redox couple. The potential between these two electrodes is then controlled by the potentiostat, and we measure the current between them. In a 3 electrode cell, we now have, in addition to a working electrode and counter electrode, which are the same as before, we now have a reference electrode, which a reference electrode is just designed to hold some specific known potential throughout a wide variety of conditions. And in a 3 electrode cell, we set the potential of the working electrode with respect to the reference electrode. So we know the potential of the working electrode. And then we allow the potential of the counter electrode to be such that it passes the same current as the working electrode. So let's first look at the performance of a solar cell performed using a 2 electrode cell. So in a standard quantum dot solar cell, we have a TiO2 QDSC working electrode on FTO glass, a sulfide polysulfide redox couple, and a copper sulfide RGO counter electrode. So if we illuminate the cell at open circuit conditions, when we don't allow any current to flow, electrons can be excited from the valence band of our QDSC into the conduction band. These excited electrons are then able to be transferred from the conduction band of QDSC into TiO2. Some of these electrons that are in the conduction band of the QDSC TiO2 recombine with holes in either the QDSC or can be scavenged by our sulfide polysulfide redox couple. Eventually, an equilibrium is reached where the rate of excitation by our incoming light is equal to the rate of recombination from the conduction bands of our QDSC TiO2. Since we're exciting electrons into the conduction band of QDSC, the steady state concentration of electrons in the conduction bands of TiO2 QDSC is increased from its dark concentration. So as we saw earlier, a higher electron population in the conduction band increases our Fermi level closer to the conduction band of our TiO2 QDSC. So this difference in between the Fermi level of the TiO2 QDSC and the potential of our redox couple is our VOC, our open circuit voltage. So if we were to imagine the same system with a larger recombination rate, this steady state concentration of electrons in the conduction bands would decrease, and this would cause a corresponding decrease in Fermi level and thus VOC. So with higher recombination rates, we have lower VOC. So as we begin to draw current from our solar cell, the counter-electrode performance begins to significantly matter. This is because the current in each electrode must be the same since they're connected in series. So in this example, the red IV curve is an IV curve for a working electrode that was taken with some ideal counter-electrode. So this is just a theoretical working electrode curve. And the blue curve is the polarization curve of a counter-electrode that we're going to be using in conjunction with this red working electrode. So when we're actually measuring our solar cell, this IV curve from our ideal working electrode and the polarization curve from our counter-electrode become convoluted. So let's see how that works. So if we imagine the case where we're drawing 10 milliamps of current from our cell, if we look at the photoelectrode, our photoelectrode can draw 10 milliamps per centimeter squared of current at a potential of about 390 millivolts. Okay, but we must also take into account the counter-electrode polarization. So if we look at this blue electrode polarization curve, in order to pass 10 milliamps per centimeter squared of current at the counter electrode, we have an overpotential loss of about 95 millivolts. So therefore, when we're actually measuring the IV characteristics of our solar cell, the potential that we'll read at a current of 10 milliamps per centimeter squared will be the 390 millivolts that our photoelectrode can provide, minus the 95 millivolt polarization of our counter electrode, so we'll actually measure 10 milliamps per centimeter squared at a potential of 295 millivolts. So if we repeat this same analysis for every different current in our IV curve, we can obtain this dashed red curve shown. And this dashed red curve is the actual IV characteristics of our solar cell. So if we were measuring a solar cell with this working electrode and this counter electrode in a 2-electrode setup, we would only ever see this dashed red line. So let's look a little bit at how energies in the cell behave when we're actually measuring IV curves. So let's start by looking at the case of an ideal counter electrode. So this electrode can pass any amount of current with no overpotential. So as we start scanning potential, starting at VOC, the current through the external circuit is 0. So the rate of recombination with our holes in our QDSC and our redox couple is equal to the rate of excitation by our incident light. So this is the same as we've seen before. So now, as we begin scanning voltage and taking our IV scan, we're decreasing the potential between our working electrode and our counter electrode. So this decreases the Fermi level in our working electrode, thus drawing current from the electrode. So as we continue to decrease the potential between these two electrodes, we continue to decrease the Fermi level of the working electrode until it reaches the potential of the counter electrode. So at this point, there's no potential difference between the working and counter electrodes. We've reached the short circuit current condition. So for an ideal counter electrode, at short circuit current, the potential of the counter electrode is equal to the potential of the redox couple. This is by definition because the counter electrode can pass any amount of current at the thermodynamic potential of the redox couple. So no matter how much current we try to draw from our cell, the counter electrode potential does not change. So now instead of an ideal counter electrode, let's look at the case where we have a very good counter electrode. Say the same copper sulfide RGO counter electrode developed in our lab. So this electrode works with very little overpotential. In this case at VOC, since there's no current flowing in the cell, the potential of this electrode is the exact same as that of the ideal electrode, so our VOC does not change. However, as we begin to draw current from the cell, we now have slight overpotential losses at the counter electrode. So we're decreasing the potential between the working electrode and the counter electrode, but the counter electrode is no longer able to stay at the same potential as our electrolyte because we have these overpotential losses due to drawing current through that electrode. As we continue to scan, we still reach short circuit current conditions when we have the Fermi level of the working electrode equal to the potential of the counter electrode. But again, the potential of the counter electrode is no longer the same as the potential of our redox couple because we have to supply this slight overpotential to the electrode. So this overpotential, as seen in the graphs in the upper right, decreases the fill factor and short circuit current of our cell. So finally, let's examine the case of a very poor counter electrode for our redox couple, platinum in this case. So again, at open circuit current conditions, since we don't have any current flowing through the cell, the performance is the same as if we had an ideal counter electrode. This changes drastically when we start to draw current through our cell. Unlike the ideal counterelectrode or our copper sulfide RGO electrode, as we begin to decrease the potential between the two electrodes and draw current, we immediately see this very large overpotential develop due to platinum's inability to regenerate our redox couple. So this causes a very large decrease in our potential seen for each individual current density, which drastically decreases our cell's fill factor. So as we continue to scan all the way to short circuit current, we now have no potential difference between our working electrode and our counterelectrode. However, the potential that these two electrodes are at is vastly different from the potential of the redox couple, because we have to supply this very large overpotential in order to get platinum to regenerate our redox couple at the rate that we need it to. So for this counterelectrode, much of the voltage of our cell is taken up by this overpotential. So we've now seen how two electrode measurements can give us real-world performance information for our solar cells. Using a two-electrode system, we're able to measure our cell open circuit voltage, short circuit current, and we're able to calculate efficiencies from these IV curves. We've also seen how individual electrode energies can change as we measure the IV characteristics of our cell, and how different electrodes can affect the performance of the system. So when making two electrode measurements, it's important to remember that the performance of the working and counter electrodes are convoluted in the measurement. So the two electrode measurements are the only way to determine overall cell performance, but it's not a good method for determining individual electrode performance because we have this convolution of both our electrodes. So if we want to measure individual electrode performance information, we have to use a 3-electrode cell. So in a 3-electrode cell, we control the potential of the working electrode with respect to the known potential of our reference electrode. This gives us direct control over the potential of our working electrode. We can then apply a potential to our counterelectrode such that the counterelectrode is able to pass the same current as our working electrode. So this ensures that the current measured between the working and counterelectrodes is controlled only by working electrode performance. So the exact nature of our counterelectrode is unimportant. So in a 3-electrode cell, the potential of the working electrode is set with respect to that of a reference electrode. The potential of the counterelectrode is set so that it passes the same current as the working electrode. So this allows us to measure the performance of the working electrode in isolation. So let's look at an example IV curve obtained using a 3-electrode cell. So the potential that we see along the x-axis is now the potential versus the reference potential. It's not absolute cell potential. So depending on the reference electrode we've chosen, this can change significantly. Therefore, to extract meaningful information about the working electrode performance, we have to convert the potential scale into a more meaningful one. So one way that we can convert this potential scale into a more meaningful one is to convert it so that the potential of the working electrode is measured with respect to the potential of our redox couple. So that is the same potential scale in effect as we saw with a 2-electrode cell if we had an ideal counterelectrode, because the ideal counterelectrode always stays at the potential of our redox couple. So to do this, we know our potential of our reference electrode, and we know the potential of our redox couple with respect to that reference electrode, so we can offset our voltage, in this case by 0.74 volts. So this gives us a new IV curve, which is the IV curve that would be obtained for a 2-electrode cell if we had an ideal counterelectrode. So this measures the performance of only the working electrode without any counter-electrode polarization effects. So using a 3-electrode cell, it's possible to determine performance characteristics of individual electrodes, providing photoelectrode IV curves or counter-electrode polarization curves. So these results can be very informative and are often important in characterizing our solar cells. But 3-electrode measurements are not able to give us information about solar cell efficiencies. So in summary, both 2-electrode and 3-electrode measurements can be used in determining quantum dot solar cell performance characteristics. Using a 2-electrode setup, the potentiostat is used to control the voltage between the working and counter electrodes. So this measurement gives us real-world performance information of the solar cell, such as solar energy conversion efficiency, our open circuit voltage, and our short circuit current. And in a 3-electrode cell, the potentiostat controls the potential of the working electrode with respect to a reference electrode, and doesn't really have any counter-electrode effects at all. So in this way, it's possible to isolate the performance of the individual solar cell electrodes, the working electrode by itself, the counter-electrode by itself, but it's not possible to determine overall device properties such as cell efficiency. So I'd like to thank you for listening to this presentation on measuring photoelectrochemical performance. I would especially like to thank those people in other groups whose research contributed greatly to this presentation. For more information on the COMET Research Group here at the University of Notre Dame, you can visit us on the web at cometlab.com. Thank you.